Hello and welcome to lecture number 17. So today we'll be studying about the 2R serial manipulator. 2R means 2 revolute joints and it has 2 degrees of freedom. It's a serial manipulator. And today we'll be doing some experiments which will include forward kinematics, inverse kinematics, then trajectory tracking. And first of all, as usual, I will explain the manual, what are the various tasks, and show the procedure, for example, how to fix the robot, and then how to change the program, and then we'll proceed to the experiments. Okay, so this is the manual for the kinematics of a 2-link serial manipulator, which is 2R or 2 revolute joints. And first is how to fix the manipulator. As you can see here is that this is a 2R manipulator which is shown. This is the top view, and we are going to fix it on a graph paper. That means we need to put the manipulator at the 0, 0 position and then draw the 2 axis coordinates x and y, so that when we are doing our forward kinematics and inverse kinematics, we can correlate where the end effector is going with respect to the joints. So the first is we are fixing the graph paper on the table. It's an A3 size graph paper which is fixed on the table. And then on the graph paper, as shown in the next figure, we are marking our x-axis and y-axis. Okay. Then on the x-axis and y-axis, we put our base plate, which is the red color U-shaped board you can see here. So this is fixed exactly at the 0 point, that is the 0, 0 of the robot, and the direction of the x and y are indicated as in the right-hand side figure. So now the first thing that you know for a robotic system before we do kinematics, we basically need the home position, or rather we need to know the 0, 0 of the base position. Okay, so this is the first activity that we are doing, is we are fixing the base of the manipulator at 0, 0, which is marked as O, and the direction in the x and y axis directions are marked. Okay, this is the first thing we do. Then we fix the robot. We insert this red color plate on the base of the robot. Okay, and then once it is attached, okay, there is a tight fit there, so we can physically fit it there, and then place the robot as shown in step 3. So we have these 4 steps: step 1, step 2, and step 3, and then step 4. Okay, so I'll be showing this as in the video also as we go along, after I finish with the manual. So in step 1, we fix the U color plate. Step 2 is we fix the U color plate, attach it tightly onto the base, the white color base. And step 3 is we align it, or rather we align the 0, 0 of the plate, which is marked as O in the previous figure, with the 0, 0 marked on the graph paper. And then what we do is there is a lever you can see at the back side, this black projection. So we press it down and fix it. So there is a vacuum cup. The orange color is a vacuum cup in step 4. So it gets tightly fixed there. So when the robot manipulator is moving, what would happen is that the base of the robot will not move. So this is the basic way by which we are fixing the 0, 0 of the robot to that on the graph paper. Okay, and making sure that it doesn't move. Then we plug in the power supply, which is the 11 volt power supply, and connect it to the operating system, that is in the microcontroller. Now, unlike the other programs where we looked at the sensor interfacing and we looked at control of servo motor, in this case we are going to run this forward kinematics, inverse kinematics using a higher level Python API. Okay, so the language is Python API, and the Python API it communicates with the microcontroller, which is the Arduino microcontroller, which is fitted on the manipulator. Okay, so for example, when we are doing the forward kinematics, inverse kinematics calculations, it will be done in the Python API, and then the values will be downloaded to the microcontroller. And the microcontroller, as you have studied, is going to control the servo motors which are fixed on the manipulator. So there are 2 smart servo motors which are fixed on joint 1 and joint 2. So these are Dynamixel smart servos. AX12A is the number of the motors. Okay, so there are 2 servo motors which are fitted onto the axis 1 and axis 2. Now, as we have seen in our previous class, the servo motors are in open loop, but by controlling by changing the PWM signal, we can actually we can control the servo motors to go and stop in a particular location. Okay, or we can control the angle by controlling the pulse width of the servo motor. Okay, so now let's look at the various tasks that we'll do today. So the first task that we'll do is to get to know. This shows the tasks and report. So first is get to know the robot operations. So we'll see the robot operation, that is very simple things like pen up, pen down, Okay, so whenever the robot end effector goes to a particular location, there is a pen at the tip. So the pen will mark on the graph paper, and then later we can measure and see whether it's correctly marked or not. Okay. The second is forward kinematics. So as you know, in forward kinematics, we'll be giving the joint angles, and the end effector will go to a particular location. Again, using the pen, we'll mark, and then we can measure on the graph paper and see whether it's gone to the right position or not. Now, the third task that we have is teach and toggle. Now, teach and toggle is basically teaching the robot to go to a particular position manually. So what we'll do is we'll disengage the motor, which means that we'll put off the torque of the motor, and then we'll take it manually, catch the or move it with your hand to a desired location, and then record that position. Then again, with your hand, you can record it. You can move the manipulator to another position, and then we can record the position, and then you can play back between those two positions. So this is something like manual teaching. Okay. Then we have inverse kinematics, which is inverse kinematics, as we have studied, is given the joint end effector position and orientation. What is the corresponding joint angles? Okay, so in inverse kinematics, we'll give the end effector position in terms of x and y coordinates, and then the program will compute the inverse kinematics joint angles and download that to the Arduino microcontroller, and the robot will move to that particular or the desired position and orientation. The third is trajectory tracking. So it can track different kind of trajectories. For example, it can track an ellipse, it can track a straight line. So the fifth task will be to track a trajectory of different kinds. Okay. The program file is, so these are the various tasks. First is, the first task is program initialization. So this is the program. This is a Python program which we have written. And the first task would be pen up and pen down. So there is a pen in the front of the manipulator at the end effector. And pen down would mean that it will mark that position. And pen up means it will lift the pen. Okay, so that is the first task that we'll be doing. Okay, so let's start off with the first task of the robot for this experiment. So first task would be initializing the program and then doing this pen up and pen down. Okay, so before that, I'll also show you, I'll show the video of the robot that is there. So this is the first program that we have. Now this program is essentially for pen up and pen down, as you can see in line number 30 and line number 32. So this is a Python program, and it is basically having at the end effector there is a small microcontroller. There is a very small servo motor which is connected with a gear to the pen. So when we do pen up and pen down, basically it rotates the pen, okay, and marks wherever when the pen is put down, it marks that position on the graph paper. Okay, so let's look at that now. Okay, so this is the 2R manipulator. You can see that this is the base of the manipulator, and this is the laptop that you can see here. The laptop is connected through the USB to the manipulator base, and this is your Arduino microcontroller which is sitting on top. Okay, so this is the Arduino microcontroller which is sitting here. Okay, so this is the Arduino microcontroller that is sitting here. And this is my 2R manipulator. So the axes are vertical. So this is a servo motor which is here. So you can see that that is a servo motor here, and there is another servo motor which is here. These are two servos. This is the end effector. So this is the end effector I was talking about, and there is a pen there. You can see that, and there is another servo motor which is holding the pen. Okay. So when we do pen up and pen down, this is going to rotate the pen position, and when we do pen down, it will go and mark the position on the graph paper. And I was talking about setting up. So this is the setup that you can see here. So the red color plate is the base plate, which is shown here, and the 0 mark is shown here. There is the 0 mark, which corresponds to the 0, 0 of the robot system, the axis system. This is my x-axis on this direction, and this is my y-axis. Okay, and this is the vacuum cup we talked about. So there is a vacuum cup here. You reduce or press down this handle, and what happens is this gets tightly attached onto the tabletop. Okay, so it doesn't move. Okay, so this is the experimental setup we have. Okay, this is so the first thing we'll do is we upload the program. So we have uploaded the program here, and what I will do is I will run the program. Okay, so that is okay. This is the position of the pen. You can see, and once we run the program, the pen will come down and put a mark on the the graph sheet, so we know exactly where it is marked. Okay, so that has come down, it has come up. Okay, so this is called the pen up and the pen down position. Okay, so in the forward kinematics program, forward kinematics gives the relation between the position xy of the end effector and the joint angles theta 1, theta 2 in this case. So what we have done is that we have removed, what we have done is we have loaded the program, and in the program you can see that it says base motor. There are two motors. There is the base motor. Look at line number 26. There is a base motor, and line number 28 is the elbow motor. Okay. So basically it says the joint angle of the base motor is 90 degrees and the elbow motor is minus 90 degrees. Okay. Now this plus and minus 90 is with reference to the x-axis. Okay. Okay. So when we run the program, basically what we'll see is that the manipulator will move and correspondingly position itself. So this is the manipulator now. So we can see that it is positioning itself at plus 90 and minus 90 of the motor. And once it reaches the position, it does a pen down and marks the position. Next one. So this is demonstrating the forward kinematics program, where we are giving the two motors, the base motor and the elbow motor, and then we are taking the end effector position to some other position. Now we can change the angles there, and if you change the angles there, we can bring it back to its original position again, or we can bring it back to the other position. So now this is on the other direction. Okay, so we have changed the angles to minus 90 and plus 90 now. Okay, and you see that it has come in position at some other position. So this is basically the forward kinematics program, which shows the relation between the end effector position and orientation with respect to the base, with respect to the joint angles. Okay. So here again we are coming back at another location, but simply by changing the angle. Okay, the next program that the next task that we have is teach and toggle mode. Now in teach and toggle, what we are doing is in teach and toggle mode, basically what the program does is it removes the torque at the motors so that we can move the manipulator with your hands. Otherwise what would happen, the motors are going to resist the motion, right? So running this program, we can remove the torque constraints on the motor and move the manipulator and then play back between 2 points. So what we'll do is we'll first run the program. Okay, so we are so first what we are doing is we are running the program. Okay, so this is the program for the torque control. So when we run the program, what happens is that the holding torque of the motors are removed. Okay. Next, what we can do is we can move the manipulator to a given location. So manually you can move it. You can see that it's moving very easily because the torque constraint has been removed. Okay. Now it is going to one position, and what we do is we can store this position in the program. Okay. So this is my position 1. Okay. And it has also marked the position 1, so you can see very clearly that it has marked the point there. Okay. So this was the point which was marked. Now the manipulator was moved to another position, or let me move it a little bit here. So maybe we move it here. Okay, I'm manually holding it and move it here. Okay. So now we have moved it to that position, and again it marks. You can see that it has marked. Oh, it didn't mark. Anyway, when it goes, it will come back. Okay. So now it has marked position 1. That was the first position. Okay, and this was the second position. Okay, that was the second position. So this basically shows that it is going from position 1 to position 2, which has been taught to the manipulator. Okay, so maybe you can run it one more time. Okay, the next task that we have is inverse kinematics. Now, as you know, inverse kinematics is the relation between the end effector position and orientation with respect to the joint angles. So what we'll be giving here is the end effector position, and the program has to automatically find out the joint angles, theta 1, theta 2. So now in this particular case, we can change the input. Okay, so the input position that has been given. So the program is in example inverse kinematics, which is this one, and the okay, here we can see that This is the starting of the program, and yeah, so these are the robot parameters, line number 32 and 33. So L1 and L2 are the link lengths, L1, L2 for this robot. The end effector position in meters is given in this line number 36 and 37. Okay, that you can see 36 and 37. So X is given as 0.2 meters and Y is given as 0.2 meters. Okay, now remember something, that in the inverse kinematics problem, we will normally find two solutions. Okay, now at the end of the workspace, the solutions merge into one solution. But in this case, we'll be getting two solutions. So it is called the elbow up and the elbow down solution. So we'll be getting two sets of solutions. So the manipulator will first go and position in one solution, then it will go and position in the second solution. Okay, so let us run the program. So this is the program for the inverse kinematics. Two solutions, 0.2, 0.2 in the X coordinate and the Y coordinate. So first you'll go and position, and it does a pen down. So exactly, you know exactly where it has gone. That was one solution, and this is the other solution. Okay, so this is the other solution. There's a slight error there, you can see, and then it comes back to. So let us change the coordinate to some other number. Let's say 0.3, 0.3 or 0.4, 0.4. So this is one position. How much is 0.3, 0.3 or 0.4? 0.3, 0.3. So this is one solution, and there is another solution which is on the other side. So that is the other solution. Okay, so here we can see that it is showing us the two solutions, okay, for the same point. Okay, so something to remember, that there are two solutions only in cases when it is completely stretched outward, then there will be only one solution. Okay, so this was the inverse kinematics task. Now the next task that we have is the trajectory tracking problem. So one is to track an ellipse. Okay, so this is the trajectory tracking problem for the ellipse. So this is the ellipse problem, where the end effector is going to track an ellipse. Okay, and after that is going to track a straight line. Okay, so this is the basic program which computes the various points of the ellipse and then executes the program. Okay, so basically it computes the position on the ellipse and then the corresponding joint angles, and positions the manipulator at the corresponding joint angles. Okay. Okay, so let's look at this one. Let's run this program. So this is the home position. From this position we are plotting okay. So look at it closely. So we can see very closely that it has plotted an ellipse. Okay, so you can see the various moves. So we can see that this is the ellipse that it has plotted, and we can connect it with a freehand drawing, of course, and then you see that this is an ellipse. Okay, this is a freehand drawing of an ellipse. Okay. So what it basically did is computed those points, these small points. Each of these points was computed, and then it did inverse kinematics to find the corresponding joint angles, and then went to those points. Okay, so this is your experiment for ellipse. The next is an experiment for the straight line motion. Okay, this is the experiment for the straight line motion. So from that point we are going to draw a straight line. Okay, so you can see that it's drawing a straight line. Okay, okay, so between 2 points it drew a straight line from the start point here to the other point, which was here. Okay, so that is the drawing the straight line. Now you can see, of course, that it's not perfectly straight. because that the motors are not very accurate. These are not DC servo motors. These are not with closed loop control motors. These are open loop control motors. Okay, so because of which it is not exactly a straight line, but it is almost a straight line. If you see the top view, we can actually calculate the deviation from a straight line because this is a graph paper. Okay, so this is the ellipse and the straight line that has been drawn by this very simple manipulator. So this is the simplest manipulator you can get, and it can be made whatever we have learned. With this you can very easily make this manipulator system. Okay, so today we finished 3 or 4 experiments, almost 4 experiments. The first one was pen up, pen down, where we looked at the various very simple program. Then we did the forward kinematics, where we gave the joint angles and it moved to an end effector position. And after that we moved to the inverse kinematics, where we gave it a particular end effector position and it computed by itself. And then after that we went to tracking an ellipse and a straight line. Okay, so this is the simplest manipulator that you can get, and it's very simple that you can make it by yourself. It's very cheap. It only has 2 servo motors, Arduino microcontroller, and we can understand the very basic fundamentals of forward kinematics and inverse kinematics.